Hi everyone. Okay, so coming back to the posterior predictive equation, remember all what we did in the previous video was about calculating the likelihood, the prior to get the posterior, but at the end, what we wanted is this, right? The probability of getting heads in the next coin toss given the data. So our posterior, which is here, was just a mechanism to get this final integral solved. So now we're going back to this integral. We call this the posterior predictive in the Bayesian setting, and we need to solve it. So we already know both terms here. Remember that the first one was theta. It was the easy one and we calculated before. And the second one is this. It's the posterior, and we already know that it's a beta distribution with those parameters. So cleaning up the screen now, we can use the PDF definition of the beta distribution. Remember, was the beta function and these factors here. So what we can do now is to replace the beta function by its definition by using the gamma functions, as you can see here. And now we can pull this term out of the integral because it doesn't depend on theta, right? Why we're doing that? Because now we can construct another beta distribution here by multiplying and dividing at the same time by this term here. We multiplied and divided by this beta function with those parameters such that here we build this new beta distribution. Why we do that? Because now having this new distribution here, if we are integrating it across the whole domain for theta, remember that theta is a probability of heads, so it lives between 0 and 1. So if we are integrating across the whole domain, the full PDF, we get 1 by a definition of every single probability density function. So these terms disappears and now we just stay with the left part. Again, we can replace the beta function by its definition with the gamma functions. And now we can simplify some things. You can see that terms go away. And also what we can do is to replace the gamma function by its factorial definition. Remember that the gamma is kind of like the factorial. The only thing we need to do is to subtract 1 in every term. So here, for example, if we subtract 1, we will end up just with the n1 plus alpha 1. So we do the same with these 4 terms, and we end up with this. Now we can use this property here in the upper right part where the n factorial is almost like n minus 1 factorial, but you need to keep the n, right? So here we could simplify these two terms. We have exactly the same case. We have like n and n minus 1 here, basically. So if we cancel both, we will end up with the last term of this factorial. Same thing with the other two terms, right? So after simplifying, we end up in this result. Okay, so this is the result of our posterior predictive. So if we go back to the main equation, we will end up with this result. And as we can see, the posterior parameters are exactly the numbers that go here in the factors, right? So basically, the posterior parameters are the main numbers that go in the final result of the posterior predictive. So let's see some insights around the posterior predictive. Recall that now we are predicting by bringing the uncertainty structure of our unknown parameter theta through the posterior distribution here. We are using the probability of theta given the data instead of using theta hat, for example, or the optimal found with maximum likelihood. In that case, note that if we decided to use the optimal hat instead of the posterior predictive, we wouldn't be Bayesians and we will have to use the optimal value, which is just counting the number of heads and divided by the total number of flips. So this is the very intuitive thing, right? If someone tells you, I flipped a coin 200 times and I got 105 heads, you would immediately go and divide that number by the 200 and you will get the estimation of your probability of heads, right? This is what we all do, but that's not being Bayesian. Instead of using that estimation, we use the whole posterior distribution. With that, we can capture the uncertainty structure of the parameter. And in general, the process of making predictions by using our model, it is often called inference, right? And it's actually being used across machine learning in many different models. So whenever we already have a model and we use it to make predictions, then we are making inference. You can see here that the posterior is like our intelligent machine that is all the time assigning a credibility value to each possible value of theta. Also wanted to mention that the posterior predictive can be seen as an expectation because it's exactly the expected value of theta in terms of the posterior distribution. Look at this equation here. What I'm saying is that this is exactly the expectation of theta in terms of this distribution. And remember that in this case, it's going to be the first parameter of our posterior divided by the sum of both. So why is this? Recall the definition of the expectation. The expectation in the continuous case is an integral over the whole domain of the variable of the multiplication between x and its distribution in case of continuous. And in case of a discrete variable, we go over every possible single value and multiply by its probability. So let's stay with the continuous case, which is our case for theta. Theta is continuous, right? This is kind of like an average, but instead of being a regular average, we are weighting by the distribution, by the PDF. So in cases the PDF is different in different zones, for example, here we can see that most of the mass is concentrated in this side. It means that the expectation of x is going to be mostly governed by this zone of x, right? So again, this is why our posterior predictive is exactly the expectation of our parameter in terms of the posterior distribution. I would like also to speak about the variance of the beta distribution. We can get some interesting insights here. Remember that the definition of the variance is this one. It depends on the expected value of the square of the variable minus the square of the expected value of the variable. And by the definition of the expectation is this. This corresponds to the first term and this corresponds to the second term. And well, we know that in this case, x is going to be a beta distributed variable with, let's say, parameters a and b, right? Recall that now we are checking the variance of any beta variable. Okay, we can replace the second term because we know already that this is exactly what we just calculated. We know that the expectation of a beta variable is this division. It's just now is the square of that, okay? Because we just saw that our result of the posterior predictive is an expectation and is exactly this term here. And this term, well, let's develop it. It's going to be the integral of the square of x, and we can replace here beta by its PDF definition, right? Here we are using the beta function again. So let's clean things up. You know that we can take out this beta function out of the integral because it doesn't depend on x in this case. And we can replace it by its definition with the gamma functions. So replacing this here, we have this result so far. Now we do the same trick we did before. We multiply and divide by this beta function in order to construct another beta PDF that is being integrated here. So this whole term is going to be 1. And we end up with this because we are replacing here the beta function by its definition, but this beta is now slightly different because it has a plus 2 and b as parameters. Okay, now we can simplify all those terms and we end up with this result. So replacing everything, we have that this is the variance, and doing some algebra, you end up in this result. So what is interesting, let's say that now the parameters of our beta distributions are what we always happen in practice, which is a combination between the imaginary counts coming from the parameter and the number of actual cases we got after a few flips. So if we replace a and b, we will end up in this result for the variance. So let's say that we start flipping the coin many and many times. We will end up with n's that are way bigger than the initial hyperparameters alphas, meaning that they will govern the final result and the alphas will start losing numerical relevance compared to the n's. So we will end up in something like this, like what we have here. And this is kind of like the approximation of the final result. We have n1 times n0, and here we have n to the power of 3. Remember that n1 plus n0 is exactly n, the total number of flips. So finally, recall that our maximum likelihood theta is exactly counting the number of heads divided by the total number of flips. So if we replace this term here, we end up in this result for our variance. What we can tell about this? Let's say that the error bars of the prediction of theta, because remember the standard deviation of our error bars are the square root of the variance, we have this term here. So what we can say here is that the uncertainty, because the error bars are exactly our uncertainty, goes down at a rate of 1 divided by the square root of n. So if you want to decrease your uncertainty, you need to do more and more flips. But instead of going down linearly with the number of flips, it's going to go down with the square root of the number of flips. It's going to be slower, right? And pay attention here. This is the plot of the variance of this term we have here. As you can see, the uncertainty is maximized when theta is equal to 0.5, and it is minimized when theta gets closer to 1 or 0. Remember, we are speaking about the estimation of our theta, our maximum likelihood. And one interesting insight out of this is the model is telling us that it's easier to be sure that the coin is biased than to be sure that the coin is fair. Because if we tell that our coin probability is 0.5, then our uncertainty gets maximized. But if we tell that if we go towards numbers that are more to the extremes of theta, like 0 or 1, then the uncertainty decreases. So this is a very interesting behavior of this model.